Next topic is potential energy and energy conversion. In previous video, we talked about what is work, what is energy, and we also talked about kinetic energy. Now we will move to potential energy, how energy is converged from one form to another form, and we will also talk about energy conservation. Potential energy is stored energy in an object because of its position or configuration. There are different kind of potential energy. Elastic potential energy is such as the energy stored in a stretched or compressed spring. uh, for example, here if we have a spring and a mass is attached at the end, and if you stretch this spring to certain distance, and if you once you release it, the spring will coil back and try to gain try to restore its original shape. And the the energy stored on this spring when you are stretching it by this displacement, uh, if this displacement is this is called elastic potential energy. And electric potential energy is because of the difference in potential between two charges. The most important potential energy in this chapter is gravitational potential energy. And gravitational potential energy is caused because of the object's position relative to the uh, reference level. And in general, the reference level is the ground or the surface. And if we have a ball somewhere high in the somewhere high here in the air, or some level, and this position with respect to the ground uh, causes these objects to store some form of energy, and that energy is called potential energy, gravitational potential energy. And if the object is released from the position, uh, the gravity will do work on them. If this object at certain height is released from its position, then the gravity will accelerate this object towards ground and increase its velocity. And that means gravity will work. And we talked about work before, where we said the force gravitational force is given by the mass of the object. And uh, since this object was held at certain height, and when we dropped this object, it traveled a distance of h. And what do we know? Work done is force times distance. That means uh, work done is work done is force times distance, and in this case distance is high. So work done is mgh, and work done on the object because of gravity is mg given by mgh. And what do we also know is that work done is equals to change in energy from previous section. And if you look at here, we said that the potential energy is based on the position. Potential energy is stored on an object based on its position relative to the ground. That means at this point the potential energy is 0 because the distance relative to the ground is 0. So change in energy is simply mgh, and the energy in this level is 0, so we can say potential energy is mgh, because there is only one level of energy, so the change in energy and the energy at that point will be the same. This is what the formula we will use for potential energy, where m is the mass of the object, g is acceleration due to gravity, and h is the height from the reference point, or we can say height from the ground level. Let's look at an example here. What is the potential energy of a 100 kilogram boulder sitting on an edge of an embankment? So we have embankment here, this is the ground level, and there is a boulder here sitting there, and the vertical distance is h. And remember that the distance is always the vertical distance, not this slanted height, rather the vertical distance from the ground level to object's position. So this is 15 meter, and we need to calculate the potential energy. Potential energy is equals to mgh. Here m is 100 kilogram, g is 10 meter per second square, and h is 15 meter, is equals to 15,000 kg meter square per second square. This is equivalent to 1 joule. We know that the unit of energy is joule, so this will be equivalent to a joule. And if you want to verify it, we can also verify it. So 1 Newton meter is equals to 1 joule. This is what we did from previous section, where we defined what is 1 joule. 1 joule is basically the work done when you apply 1 Newton of force to move an object by 1 meter, right? So if we want to simplify this, 1 joule is equals to Newton is, so where does Newton come from? This is where we started using Newton from. So F is equals to ma. M is mass, so it should be kilogram, and A is meter per second square, because it's an acceleration. That means 1 joule is kg meter per second square, and this is meter, so kg meter square per second square, which is what we have here. So we can simply if you are using all these units in SI units, then you can simply write any form of energy in joule. So basically the potential energy is 15,000 joule. And the conservation of energy, this is one of the most fundamental principle in physics, and where you probably have already heard about this. Energy is never created or destroyed. Energy can be converted from one form to another form, but the total energy of the system will always remain constant, and this is what conservation of energy, this is what we call conservation of energy. And we just said here, energy is never created or destroyed, but it's converted from one form to another form, and the total energy will always remains constant. And let's look here. For example, we have a simple pendulum here, and it's raised to certain height of h from the reference point. So here the original position of this the uh, equilibrium position of this spring is sorry, the pendulum is taken as a reference. That means the potential energy at this point is zero, because h is equals to 0. And if you look at this pendulum systems, say we raise this ball first at this point, and if you look at here, since this ball is not moving yet because it's about we are about to drop it, right? So there's no velocity, that means kinetic energy is 0. But we raised it by certain height h, that means potential, there is some potential energy given by mgh. And since there is no kinetic energy and only potential energy, total energy is given by kinetic energy alone. So we can say this is 100% kinetic, 100% potential energy and 0% kinetic energy. Now as the ball is moving this way, it will, because of gravity, there will be some acceleration on the ball, and there will be some, if there's an acceleration, there will be some velocity on this ball. And if we have a velocity, we also have kinetic energy. And if you look at this is a halfway from this original height. That means potential energy compared to this position, the height is half, so we will have half of potential energy. And we also said that the total will remain same. If half is potential energy, then the other remaining half should be kinetic energy. And at this point, at the equilibrium position, the height from the reference point is 0, so there's no potential energy. But we know that the total energy should remain constant, so there will be 100% of kinetic energy. So energy is converted from one form to another form, and in this example, from kinetic energy to potential energy, and from potential energy to kinetic energy, because of the in because of the acceleration due to gravity, potential energy is converted into kinetic energy, and kinetic energy is converted into potential energy. And this kind of forces that causes energy change in energy, that can be conserved are called conservative forces. And you should note that some of the forces, some of this effect are not conservative. For example, you are rolling a ball in a inclined surface, right? This is rolling down. When it's rolling, there will be friction between the ball and the surface, and friction generates heat. So there will be some energy loss because of this heat. There will be some heat caused by this friction, and that heat energy we cannot reverse it back to other form. So it's generally called non-conservative energy, because we cannot change that heat energy back to the potential energy or kinetic energy of the object. And let's look at an example for the conservation of energy. Now we know that the total energy of a system will remain constant, meaning kinetic energy plus potential energy will be a constant number. And let's look at the same example we did before. We have a boulder at an height of 15 meter, and let's say that this ball is dropped from the height, and we need to calculate the velocity of this boulder when it is just about to hit the ground. So after it hits the ground, the velocity, if we neglect the collision, if we are not interested in collision or the boulder bouncing back, we can say that the velocity will be zero because it will be at rest, right? That means we are interested in the velocity when the boulder is just about to hit the ground. Now if we go back to our conservation of energy, we know the total energy will remain constant within the system at this top position. Initially the boulder was at rest. That means no velocity, right? No velocity means no uh, kinetic energy, and we will have potential energy given by mgh. So here mass is this is the problem from the previous example. So mass is 100 kilogram, height is 15 meter. So potential energy is 100 kilograms times g is 10 meter per second square, and height is 15 meters. So total potential energy is 15,000 joule. And using the conservation of energy, total energy at the top of this embankment is potential energy plus kinetic energy, and kinetic energy is 0. So 15,000 joule plus 0 is 15,000 joule. Now at the bottom, when it's just about to hit the ground, what do we know? The height is 0. That means potential energy is 0, and there will be kinetic energy because when this ball is dropped from the top, gravity will do some work on the boulder and it will increase its motion, meaning we will have some velocity on the object. And if we go back to conservation of energy, total energy is kinetic energy plus potential energy at the bottom, and there's no potential energy because height is 0. So potential energy is 0, and kinetic energy is half mv square. And what do we know? We know that the total energy remains constant, so this total energy is the same as the total energy at the top position. So if we use this relation, what do we get? Half mv squared is equals to 15,000 joule. And if we want to calculate velocity, we can isolate this v square will be 2 times 15,000 joule over m. And if you look at here, there's a square, so in order to remove square, we can take a square root on both sides. And this is v. And if you calculate if you put this number in calculator, you will get 17.3 meter per second. So in conclusion, we using conservation of energy, we can calculate the velocity of the boulder, just before it hits the ground. Uh, uh, However, we should also remember that some non-conservative energy are also there, and one of the most prominent example of non-conservative energy is uh, the heat energy, uh, because of friction.